Hi everyone. So this video is going to cover the basic ideas of the section on the integral test, which is section 11.3. So the integral test is the first test that we get that is designed to answer the question when a series converges when we don't necessarily have an easy way to come up with a formula for the nth partial sum. So remember, if we have an nth partial sum, then we could take a limit, we could actually figure out what a series adds up to. Generally, it's the case that, generally, we don't know what a series adds up to. And so if we're dealing with series that we haven't, that aren't in a form that we've already seen before, it's a geometric series where we actually know what they add up to, or a telescoping series where the middle falls out, then we're sort of on our own. We have to have other tools we can use. So at this point in the course, we've looked at geometric series, which are things of the form AR to the n minus 1. And remember that these add up to A over 1 minus R. We looked at telescoping series. And more broadly, series where we can actually get a formula for Sn. So with a telescoping series, the middle terms all disappeared. And we ended up computing a limit as n went to infinity of a formula for the nth partial sum. So this requires a formula for Sn. But unfortunately, most of the series that we come across in practice are not series that have simple forms like this. And some very basic ones, some very, very fundamental series can't be approached from this standpoint at all. So what are we going to do with things that look like, for example, so this is going to be our motivating example for the section. We're going to look at the series 1 over n squared, and we're going to look at the series 1 over the square root of n. And these are both examples of series that are called p-series. So what we're going to be developing here is a theory of series that look like the sum of 1 over n to the p when they converge and when they diverge. So that's the goal. So we're going to be looking at convergence of these. And from what we develop in our study of this type of series, we're going to get a test that we can use on a broad family of different kinds of series that are determined by functions. So if we start by looking at, say, the sums of the reciprocals of the squares, so 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so on, we can actually see, I mean, just from the standpoint of looking at the sigma notation, I guess here I should say 1 to infinity, that the nth term an is determined by this 1 over n squared, but really we can think of that as f of x. So there's this function 1 over x squared that we're plugging n's into that's creating this series. And so because we're going to be integrating, we need to have a function that can be integrated. So we're going to require that the f's here are continuous that produce the series. And this is a continuous function. So what I'm going to do is I'm going to plot this function, and I'm going to plot the dots that it spits out as the terms of the series that we're adding up. So if we plot this, 1, 2, 3, 4, and we plot the function f of x is equal to 1 over x squared, we get something that looks like this. So it starts at 1, 1, and by the time it gets to 4, it's all the way down at 1/16. So it kind of does this, tending to 0, and the points of the series, the terms of the series, fall at those positions on the curve. So sort of the move that we make here is we notice that if we can use the curve to approximate the series by thinking about the series as determining the area of a bunch of rectangles. So this will be easier than on the blackboard in class because I have access to more colors and more pen effects. So what I'm going to do is I'm going to think about this rectangle right here. And that rectangle has area, well, its width is 1, and its height is whatever the value was at 2 here, which was at height 1/4. Notice that corresponds to this term right here. So the area of this thing is 1 times 1/4, which is just 1/4. So this rectangle corresponds, this area of this rectangle corresponds to that term in the series. And if I draw another rectangle here, well, this rectangle has area 1/9 because that's the height of the graph right there. So that corresponds to that term of the series. And so what we're saying is each one of these rectangles corresponds to one of the terms in the series, except for this one. So we'll just leave that off to the side for a second as a 1, because 1 isn't going to change whether or not a series converges. And we'll notice that for all of the rest of the terms, the area of these rectangles is trapped underneath the red curve. And the last observation that we need to make is that this integral, if I took the integral from 1 to infinity of 1 over x squared dx, it's improper, but this is finite. So we learned that in the improper integral section of the Calculus 2, this is in chapter 10, that if I have 1 over x squared, 2 is bigger than 1, and so that integral converges. So the big theme here is that if I'm smaller than something finite, I must also be finite. So the upshot of what I've written here is that the series 1 over n squared can be thought of as 1 over 1 squared plus a whole bunch of areas of rectangles, and the area of all of those rectangles together is less than or equal to 1 plus the integral from 1 to infinity of 1 over x squared dx. And that integral is 1. So what we're saying then, since everything here was positive, is that because this converged to a finite number, this 2, this is finite, then this must also have converged because it adds up to something smaller than infinity. There's actually one more step that we need to make here, which is that if you think about the sequence S1, S2, S3, which remember corresponds to A1, A1 plus A2, A1 plus A2 plus A3, all of those terms are positive, and so this is an increasing sequence. It's increasing because each time I'm adding another positive piece to the end, so I'm making it bigger. So it's increasing, but it's also bounded. And a sequence that is increasing and bounded must converge. Increasing and bounded must converge. That was the last theorem that we pointed out in the sequence section, was that any sequence that is monotone and bounded must converge. This is where that theorem is applied. Okay. So it seems kind of like a cheater's trick to think about the series as arising from this pile of rectangles, but if I can think about it that way and show that if I think about the rectangles in such a way that we can show that they're smaller in total area than something that is finite, then those areas must have added up to something finite. And now we're going to use another cheesy trick to show that the other series, this 1 over root n, is going to be larger than something infinite. So now let's think about 1 over the square root of n, which obviously arises from the function f of x is equal to 1 over root x, or if you like, you can think about that as 1 over x to the 1/2. Then we're going to do the same exact thing. So we can plot this series. So 1 over root x looks like 2, 3, 4, starts at 1, 1, just like the other function does, and it goes to infinity. It goes to 0, but it goes to 0 a lot slower than the other one does. And as before, we can plot the points that represent the terms of the series on here. Now the difference between this problem and the last exercise is that this area in here, this area is infinite. And what I mean by that is the integral from 1 to infinity of 1 over the square root of x dx is divergent. That's not an integral that exists. So if we could show that the series 1 over 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4 could be thought of as a bunch of rectangles whose area is bigger than the area contained over the function 1 over root x, then the fact that this is infinite would force that to be infinite as well. And the way we do it is we just reverse the way we draw the rectangles. This rectangle right here has width 1 and height 1, so it has area 1, and that corresponds to that term right there. This rectangle has height 1 over root 2 and width 1, so its area is 1 over root 2, which means it corresponds to that term. This rectangle has area 1 over root 3 because it has height 1 over root 3 and width 1, so its area corresponds to that. So the idea here is that whatever this series happens to be, it must be larger than the integral from 1 to infinity of 1 over root x dx. It has to be, because the rectangles, when you add them all up, I've drawn this one incorrectly, the rectangles, when you add them all up, they're all over, they're all over the curve this time. So the rectangles are an overestimate for the area contained under the curve. So whatever their area happens to be, it must be larger than the area contained underneath 1 over root x, which is infinite, and so the whole thing is infinite. And so this must diverge. Okay? So smaller than something finite meant that you were finite. Larger than something infinite means you're infinite. And that's basically what the integral test says. So the theorem says is that this idea works on lots of series, subject to certain conditions that allow us to integrate the function. So suppose that you have a function f of x, which is continuous, positive, and decreasing. Then the sum, I guess we should say also, and there's a series, an is equal to f of n. Then the sum from n equals 1 to infinity of an converges if and only if which means it's a precise equivalence. They both converge or they both diverge. The integral from 1 to infinity of f of x dx converges. So studying the series is the same as studying the integral. And really, technically, I can start the integral anywhere because what I care about is that the asymptotic behavior of the function converges to something. Okay, so really that one could be an a, and sometimes it will be convenient to let it be 2 or 3 or 1,000 or whatever. But this is the basic idea. Once I check these 3 conditions on the function that I'm working with, then I can integrate the function from some number to infinity as an improper integral, and if that exists, then the series converged, and if it doesn't exist, then the series diverged. So let me do a quick example here. So the sum from n equals 1 to infinity, say, of the natural log of n over n. Now that's not something we have any access to. I will point out that because I'm trying to make it a theme that we suspect whether a series converges or diverges when we start computing it, we should suspect that this is a divergent series. And the reason we should suspect that is because we're supposed to remember that 1 over n, which is the harmonic series, diverges. If I add these up, this is divergent. But 1 over n is smaller than the natural log of n over n. The natural log of n is larger than 1 for all values of n bigger than e. And so what that means is this thing, each individual piece of this series is bigger than each individual piece of this one, the corresponding pieces. This series diverged, and bigger than infinite should also be infinite. So we should suspect that the sum of the natural log of n over n diverges. That's not a proof, it's just a suspicion, and we're going to verify that with math. Now, to apply the integral test, I actually need to make sure that the function that makes the series satisfies all the conditions that I set. Continuous, positive, and decreasing. So it's definitely the case that f of x is equal to the natural log of x over x is continuous, because the values that we're putting in here are every 1 and larger. Right? It's a continuous function. 2, it's definitely positive, because the negative values of the natural log happen between 0 and 1, and we're never putting anything in less than 1. That's true. To show that f of x is decreasing, the typical way we do that is we're going to use the derivative. So a function decreases if it has a negative derivative. So if I compute f prime of x, I'm going to end up with 1 minus the natural log of x over x squared. The bottom of that function is always positive. So what I care about now is, when is this negative? Well, 1 minus natural log of x is negative whenever 1 is less than the natural log of x. And that will happen for all values x bigger than e. So I don't care if it's for all x, but what I mean by decreasing is there has to be a point at which the function is always decreasing past that point. Okay? So this function has a negative derivative for every value of n larger than e, which really means anything bigger than 2. And so this is eventually decreasing. And really, once it starts decreasing, it decreases forever because it has a negative derivative. And that means that I've satisfied the conditions I need to apply the integral test. So continue the example. The integral from 1 to infinity of the natural log of x over x dx. Make sure that when you're doing these exercises that you don't treat infinity like a number. I'm going to keep reminding you. This is a pretty typical u substitution, so you let u equal the natural log of x. So you get the limit as t goes to infinity of the integral from 0 to the natural log of t of u du, which gets you the limit as t goes to infinity of 1/2 u squared evaluated from 0 to log t, which is the limit as t goes to infinity of 1/2 times the natural log of t squared, which is infinite. Since this was divergent, we know this diverges by the integral test. So that's the sort of walkthrough of the steps that you need to actually apply an integral test. You satisfy the 3 conditions. So you must know the function that gives you the series, the function that dictates the terms are continuous, positive, and decreasing. And then you know that whatever the integral does, the series also does. Since the integral diverged, the series diverges. So using the integral test on series of this form, these are the p series, allows you to classify them into 2 families. So the first family is the divergent p series. So we say that this converges when p is bigger than 1, and it diverges if p is less than or equal to 1. And famously, of course, remember, this includes the harmonic series, because the sum of 1 over n, which is the harmonic series, is equal to the sum of 1 over n to the first, which is the p series with p equals 1. So it's included in this family and divergent. Notice that this also picks up the first 2 motivating examples that we looked at. So if we look at the sum of 1 over n squared, this has p is equal to 2, and therefore it converges. If we look at the sum of 1 over n to the 1/2, that's p is equal to 1/2, and therefore divergent. Okay. And the p series are important enough that you're supposed to be able to identify just by looking at the series if you think it converges or diverges. That should not be something you have to think hard about. If I see 1 over n cubed, I should just know that's convergent because it's a p-series with p equals 3. Okay, so I actually am going to split these videos. This covers the first part of the integral test, p-series, an example of using the integral test, including checking all the conditions. In the next video, what I'm going to talk about is using the integral test to approximate what a series adds up to. So in general, the integral test is not going to tell us the value of a series, but we can use the integral test to tell us how good our approximations are if we do a partial sum approximation of a power series. All right, so that concludes this video with the first part 11.3. In the next part, we'll talk about approximation, and I'll talk to you guys later.